Hi ladies and gentlemen, we're going to take a look at Hopital's rule today, and what I want to do is just provide a little bit more emphasis on what the idea behind Hopital's rule is. There will be plenty of opportunity for you to read and practice the execution, the skills associated with Hopital's rule. I want you to understand the idea. The idea is really important. Alright, so here's Hopital's rule. Again, I've taken this and modified it from Wikipedia. And what I want to do is just take a look through what it says. It says if we have a couple of functions f and g that are differentiable on an open interval I, so just think some kind of open interval a to b, and it says except for a point c that's contained inside of the interval, moreover, the limit of the function of f is equal to the limit of function of g, and it's equal to 0, or they're equal to infinity, or they're equal to negative infinity. If the limits of both of those functions are equal to the same thing, 0, infinity, or negative infinity, then, and it says that we have to have the derivative non-zero, which makes sense because the derivative is going to be in the denominator. Then what we have is that the limit, as long as it exists, is the same between the ratio of f and g and the ratio of the derivatives of f and g. So this seems pretty straightforward, and it pretty much is. The real question is why? Why is this a true statement? Before we answer that question, I wanted to show you that you've already been doing this, you just didn't realize it. I have an example here in yellow. And this example is a cubic polynomial over a cubic polynomial x going to infinity. So what we have is we have the numerator, which over here is the f portion of the problem. That is going to infinity as x goes to infinity. The same is true of the denominator. So really what we have is something that looks like infinity divided by infinity. And this is exactly the type of situation where we use Hopital's rule. Now you've already done this problem, and the way you did it was by multiplying the numerator and denominator by 1 over x cubed. Let me briefly write down what that gives us. So after a little bit of algebra, we have this, and then we know, and you've been doing this for a couple of weeks, that we're going to end up with these terms, right? These are all going to 0 here. That's going to 0, that's going to 0. And what's left then is the 1/2, which are the coefficients for the highest order, and you know this. Let's apply Hopital's rule to this, however, since it's an infinity over infinity ratio. Hopital's rule tells us that this limit here, this one, is equal to the limit as x goes to infinity of the derivatives. So that would be 3x squared plus 2x divided by 6x squared plus 1. Well, this is another situation where I have infinity over infinity. So I take the derivatives again. Hopital's rule still applies. The functions are still differentiable, and I still have this indeterminate form of infinity divided by infinity. So if I take the derivative again, then I have the limit as x goes to infinity of 6x plus 2 all over 12x. And again, it's infinity over infinity, so I end up with the limit as x goes to infinity of, taking the derivative one more time, 6 over 12, which of course is just equal to 1/2. The answer has to be the same because it was correct the first time around. This is Hopital's rule. It tells us that the ratio of those derivatives gives us the same limit. Now, you're asking yourself, why do you care? You were able to do this problem previously. I'm not going to disagree with you, but let me give you another problem to consider. Here's our problem, this time in cyan. And what we have is, again, we have something that's going as infinity over infinity, because as x goes to infinity, the numerator is going to infinity, and so is the denominator. In this situation, I can't use any clever algebra to simplify. I can't mix the polynomials of x with the exponential e to the x. I'm not going to get any headway if I try to do that. So I'm going to apply L'Hopital's rule. Applying L'Hopital's rule tells me that this limit is equal to, it's the same thing as taking the derivative of the numerator, 3x squared plus 1, all over derivative of e to the x is e to the x. Again, I have infinity over infinity, so I'm going to take the derivative again. And this is the limit as x goes to infinity. And I'm going to have to take the derivative 2 more times, so let me just do this quickly. So I've taken the derivative of the numerator 2 more times. Derivative of 3x squared plus 1 is 6x. Derivative of 6x is 6. Now I have something where I don't have infinity over infinity when I'm taking this limit. So this limit is equal to, it's equal to the limit. I'm going to pull the 6 out in front as x goes to infinity of 1 over e to the x, which is equal to, and that limit is going to 0. So 0 times 6 is going to give me 0. So here's a problem where I was not able to solve it using my standard approach. Let me give you another example. All right, so now I have this example in green. This is limit as x goes to infinity of x cubed plus x divided by natural log of x. Again, both the numerator and denominator are going to infinity. But let's apply L'Hopital's rule and see what we get. L'Hopital's rule tells us that this is equal to the limit as x goes to infinity of the derivative, 3x squared plus 1, divided by derivative of natural log, which is 1 over x. Simplifying, I can have the limit as x goes to infinity of, and now what I'm going to end up with is 3x cubed plus x. And this is going toward infinity. So this is the way in which I can use L'Hopital's rule to help me find limits. One more example, and then we'll get to what's actually happening here. So my last example here, x is approaching 0. This is the case. Remember, we could have infinity over infinity, or we could have 0 over 0. This is the situation here. Sine of 0 is 0, so as x approaches 0, the numerator is approaching 0, but so is the denominator. L'Hopital's rule tells us that that is equal to, and I can differentiate the numerator and denominator. So the limit as x approaches 0 of derivative of sine is cosine, and then derivative of the denominator is 2. Now I have something that I can evaluate. In this situation, the numerator is going towards 1, cosine is approaching 1 as x approaches 0, and the denominator is just 2. So this is equal to 1/2. Again, I'm using L'Hopital's rule as a means of doing the calculation. Let's go back to what L'Hopital's rule is actually saying to us. This is the critical piece. So L'Hopital's rule is telling us, go back to what derivatives are. You must keep straight in your mind what the meaning of derivatives are. They are rates of change. L'Hopital's rule is telling us that if the two functions are both going to 0 or both going to infinity, the value of the limit has to do with the rate at which they are going to 0 or infinity, respectively. The one that's going faster is going to dominate what's happening. So what we see with the exponential is the polynomial function x cubed plus x is going to infinity, but it's going slowly compared to the exponential e to the x. E to the x is a faster function. And because it is going to infinity faster, the limit of this ratio turns out to be 0. Kind of the opposite is true for natural log. So natural log, remember logarithms are exponents. And the exponents are increasing really slowly. So again, we're comparing the polynomial function to the exponent. That's what logarithms are. The logarithm is a slow function. So the numerator is going to infinity faster than the denominator. And because the numerator is going to infinity faster, the result of the limit is it's infinite. It's really a means of balancing which functions are moving faster. And if there's a tie at the first derivative level, we take the second derivative. If there's a tie at the second derivative level, we take the third derivative. That's what we saw up here with this first example, which you've been doing with algebra. So finally, let me just summarize something that's really important to keep in mind. There's a distinct ordering of the pace of functions. The natural log function is really slow. It is much, much slower than any polynomial. Any function that looks like x to the n is going to be faster. Polynomials are really slow compared to any kind of exponential function. Exponential functions are very slow compared to factorials. And factorials are very slow compared to the function x to the x. So this sequencing of rate, and remember, derivatives are rates of change. So derivatives are directly related to what we're talking about here, hence L'Hopital's rule. This is an ordering of the speed at which these functions are actually going to infinity. Okay, the fastest functions are over here on the right, and the slowest functions over here on the left. That's it. Thanks.